Hello, welcome to today's AWS webinar, Journey Through the Cloud. Today's topic is application services, or running and consuming services that wrap software or traditional software that's installed into environments such as EC2. This is a continuation of our Journey Through the Cloud series. If you wish to find out previous webinars, you can search our YouTube channel and see recordings for all of these. And these slides and indeed a recording of this webinar will be available via SlideShare and YouTube afterwards. My name's Ryan and I'm a technical evangelist at AWS, so I'm going to take you through this webinar today. And you can catch me on Twitter at RyanAWS. So the Journey Through the Cloud series of webinars is designed really to demonstrate common use cases and stepping stones that customers have taken into the AWS cloud. Learning from the customer journeys that others have taken, learning from how they've consumed the services in AWS to take advantage of them in their own projects, and picking up a bit of best practice that you may use to bootstrap your projects and your journey into AWS. Now today's topic is application services. And this is all about building upon the services that have been built for the cloud and that are run by AWS on your behalf. And these are services that try to address common pain points in your application architectures, such as operating databases or middleware. And the idea is that we can reduce the operational burden placed upon yourselves by managing those software components for you, enabling you to focus on the application function that you're designing and building, not the undifferentiated heavy lifting associated with running common application components, common middleware, data stores, and so on. So with that in mind, the agenda today is to take a look at why AWS is a good place for consuming application services. We're going to dive into the services at a top level and then select a few of those services we're going to deep dive on. So we're going to look at how they work and how they would compare to running those sorts of software as a services in the cloud yourself. And then we'll give you some ideas on where to go next at the end. And we'll drop in case studies where we can so you can get an idea of the sort of customers that are consuming the sorts of services we're talking about today. So why AWS for application services? Let's start with a definition. So what do we mean by application services? I think generally we'll talk about these as being services that wrap software you commonly install and manage yourself. So that could be anything from running a database platform, an email server, a search engine, a piece of middleware, a piece of workflow. Application services to AWS can cover a broad range of topics, such as databases, middleware, frameworks, and analytics. And we're going to dive into each of these in turn through the presentation to look at the types of services we have, from RDS to EMR to middleware such as Simple Workflow and SQS. Now, what the challenges that are common with application services are that those are the common with running any sort of application, namely scalability, reliability, and availability. And if you find yourself focusing on the task of scaling a framework that you're maybe running to perform a function within your application rather than optimizing your code for scalability or your side of the argument for architectural scalability, or if you find yourself suffering from reliability of components that you're using to build your application that are affecting the overall performance of your application. Or you're spending a lot of time scaling middleware and making it highly available and fault tolerant, if you like, the glue between application components. If you're decoupling your architecture, then that glue needs to be as reliable as the components that surround it. And if any of these sort of questions ring true for you, then you may consider running or consuming an application service as opposed to installing and managing that software yourself. Another challenge with application services is the operational management. It's one thing thinking about the architecture and design and how you make these things reliable, available, and scalable, but you've got to manage stuff as well. So are you spending more time managing application services than you do building and managing the application that's core to your business? Then you want to think about consuming these things as a service. Just as you would maybe consume email services as a service in your business to use your back-end email server rather than running an email server yourself, think of the components that build your applications in a similar sort of way. When we speak to customers, and customers can be anything from the startups through to Amazon retail organization themselves who run on AWS, we're often brought back to this statistic that 70% of the time spent in running an application, particularly in on-premise environments, is performing undifferentiated heavy lifting. So doing all the muck associated with making stuff run, as opposed to the 30% of your time focusing on your business. And we can flip that with cloud-based infrastructure, and in particular when you start to consume core components as services rather than installing and managing software to do those things yourselves. You spend less time configuring assets, in this case cloud assets, and more time focusing on your business. And this is a common theme that we're going to see through today's webinar when we talk about the individual services on offer and how they can affect the dynamic in your DevOps teams. And if you think about how cloud services are constructed, everything from compute through security, networking, monitoring, and so on, infrastructure and application services, they're building blocks for building applications. And they are designed and built from the ground up for the cloud and available at the end of a web service. So just as you would consume maybe an EC2 instance to perform a particular task, and you might consider that instance to be disposable when you finish that job, and you would expect that things like S3, our simple storage platform, are built for very high durability of objects. We'll see the same sort of properties of durability, of reliability, of scalability applied to application services such as databases, such as messaging middleware and workflows. And that's going to be, again, a common theme that we'll see through today's presentation. So some of the customers that use application service in AWS, there's many and they're varied, but I've tried to pick 4 here that give a good spread. So if you look at Sega focus on using RDS to power their online forums and some of the multiplayer games that they have. We'll look at that case study in a bit more detail later. Shazam, the popular music and tagging application, used DynamoDB, so a managed NoSQL database to bring on massive capacity. And the case study we talk around is handling a demand peak during the Super Bowl, a huge peak in demand, and they were able to scale up by simply issuing a command to Dynamo as opposed to dealing with the operational side of life of dealing with a NoSQL cluster themselves. SmugMug allow themselves to focus on their application and architecture as opposed to running very large search clusters by using cloud search. So SmugMug is a photo sharing and tagging application. And in the world of scientific research, Sage Bionetworks rely on simple workflow to orchestrate some very complicated and heterogeneous scientific workflows across collaborators and across different companies. So coordinating a pipeline of processing to deal with biomedical research. So quite varied, from RDS, from a relational database as a service, through NoSQL data stores, through search engines to workflow and coordination and orchestration. And we're going to look at those services in turn in a moment. Now, you might be able to, by consuming a service, reduce costs. Okay, so running software on EC2 can be more expensive than consuming that same functionality as a service. And when we look at some of the examples, you'll see some obvious ones where you might run and consume a queue, and you might need an EC2 instance to run a queuing service to decouple applications. Now, consuming that queue as part of a service means that you can stop running that EC2 instance, and therefore you save costs. So a very basic cost-saving mechanism there. You can improve reliability because the services we'll talk about are built with inherent multi-AZ functionality, so multi-availability zone regional level services can help improve your overall application reliability. You can scale more easily. So these services built at a regional level and built across multi-AZ and built with auto-scaling in mind mean that they can scale for you, and you don't have to put the effort in designing software and installing configurations that will scale. We take care of that, and you don't need to invest in infrastructure or software or licenses to do it. We just take care of that behind the scenes. And you can refocus your energy, so you can spend less time doing undifferentiated heavy lifting as a result and spend more time on your business. So an example of that in action is a queuing. So as I just described, so take a typical example where we have 2 applications, the 2 top yellow boxes, that are needing to talk to each other, and you're decoupled architecturally via a persistent message queue, enabling you to create fault tolerance and architectural isolation between the application components that are doing particular tasks. So in this case, I've installed some sort of queuing software on the instance. And I've installed an instance in an availability zone. So I've effectively got 3 EC2 instances, 2 of them running my application components and 1 of them running a piece of middleware. Now, if I want to make that fault tolerant and highly available, then I would start to spread things across multiple availability zones, where I've got 3 queues, each an individual availability zone running on a server, and I've got to then implement some technical process where that queue is shared or clustered across multiple availability zones so that I can treat my entire application as a whole across the region as being fault tolerant. With a software service, and in this case we're going to talk about SQS, I can remove the software running on EC2. So I can get rid of the queues that I've installed, I can save myself some EC2 costs, and I can replace it with a regional service running in AWS called SQS. So I can simplify the operations in each availability zone. I don't have to run EC2 instances and manage and monitor those. I've saved some cost and I've improved my overall reliability as a result, because SQS is by definition a regional service that's highly durable and highly scalable. So queuing on AWS, if you did it yourself, you might set up and manage some instances. You're going to install and configure some messaging middleware of your chosen flavor. You might then have to set up a persistent message store behind that, be that a database or a file system. Then think about clustering across availability zones so you can achieve some sort of high availability configuration in best practice. Then you might need to start monitoring that application framework and the queuing system you put on those EC2 instances, and then you can start to consume and use those queues in your applications. Versus with Amazon SQS, simply creating a queue from the console or from the APIs or CLI tools, and then using an HTTP boot to place messages on the queue, or an HTTP GET, and recently we've supported long polling for SQS to pull messages off the queue. And you get all the configuration in the UI, or the command line, or the API to handle things like message locking and so on, to ensure you get consistent guaranteed delivery of messages between an application and another. So a greatly simplified approach and a very cost-effective and scalable approach. Let's look at some of the application services. That was an example of SQS, but there are other application services in AWS. So looking at databases on the left, we have a relational database service wrapping a classic RDBMS system, and we'll look at that from Oracle, MySQL, and MS SQL in a second. We've got SimpleDB, which is a lightweight object store that enables you to do a NoSQL-like framework, but highly indexed. So really very flexible and great for small-scale storing of different things like session states or average sort of size payloads that you might want to put in a non-relational store. Through to DynamoDB, which is a hugely scalable, highly scalable NoSQL store with a restricted indexing paradigm on top of it. So like SimpleDB, but going to a much greater scale. So similar to things like MongoDB or Cassandra. Through middleware, so we have caching software, which is a memcached framework called Elasticache. So whereas you would maybe typically install a memcached cluster, you can consume Memcache as a service from Elasticache, and we'll take care of installing the EC2 instances, installing the software, managing the cluster across multiple availability zones to give you a highly available performant cache. Simple queuing service, which you've just seen. So think of simple queuing service as replacing the need to, let's say, use a JMS provider and back that onto a database, for example, and to make that message store persistent in your environment. Through simple notification service, which is a pub-sub framework. So similar to some of the concepts you might see in a classic JMS or message queuing framework that enables you to do publish and subscribe. Simple notification service provides that functionality as a service. So you can subscribe to topics, and topics can create alarms that you can drive through AWS, and then you can post results to an HTTP endpoint or send emails. So you can drive pub-sub with simple notification service. Simple workflow is the ability for you to manage long-running state without having to install software to do that. And we've got some specific examples of simple workflow in this presentation. And then there's frameworks. So try to position these as more application level frameworks to perform a specific function in your application. So Cloud Search replaces things like OpenSearch, Solr, Lucene type search indexes. Again, that at scale you have to manage multiple instances and manage clusters and manage the tuning of them. And then Simple Email Service, replacing the need for you to install email services. CloudWatch is a monitoring framework, so you can leverage CloudWatch to do the monitoring of your assets within AWS, from EC2 instances to load balancing through databases. But you can also publish your own data to CloudWatch. So maybe rather than installing a monitoring framework, if you're starting from scratch in AWS, leverage CloudWatch from the off, and then you don't have to worry about installing probes or running servers to deal with CloudWatch with monitoring framework data. And then at the far right, we have analytics. So Elastic MapReduce is our Hadoop as a service. And the services we're going to drill down on today are Relational Database Service, DynamoDB, Simple Workflow, Cloud Search, and EMR, Elastic MapReduce. So we're going to go deep on those services, explain the differences between them and doing it yourself, and give you some examples and show you how they work. So the first of those we're going to drop down to is RDS, Amazon Relational Database Service. So if you think about running a database, the sorts of things that you need to do or that you get involved with when you start installing a relational database platform, and this is a Forrester breakdown of the effort you'll expend. So the big chunks of time are spent doing backup and recovery tasks, they're 20% of your time in grey, performance tuning in purple going anti-clockwise, and then the installation of service of the platform, upgrade management, patching of the underlying database platform, and performing data migrations to and from different versions. So the vast majority of the time is spent doing what we call undifferentiated heavy lifting. These are things that don't differentiate you or your application. They're simply there to support the maintenance and the running of a database platform. They're not there with the database engine sort of content that you want to put in there that drives your application on top. So all the sorts of tasks that we hear, from migration, backup and recovery, software upgrades, frequent server upgrades, versus things like schema design, query optimization, or query construction, you want to spend more time focusing on those things, the design, the construction of the queries, the optimization of those queries, providing business functionality and logic to your apps, versus doing the muck, the undifferentiated heavy lifting. So migration, patching, configuration, upgrades, dealing with hardware problems, and so on and so forth. Now, RDS allows you to take away that undifferentiated heavy lifting. So it's a near zero administration platform. So effectively, you create an AWS RDS instance, and we manage the EC2 instance behind the scenes. You choose your database platform, it can be Oracle, MySQL, or MS SQL currently, and you choose the size. And we'll take care of the patching, the upgrade of that platform in maintenance windows you define. We'll tie the database into our monitoring framework so you can pull a load of metrics and alarms out of the database. And importantly, you can do one-click high availability. So by choosing a multi-AZ deployment, here is the console for RDS, we can see that I can choose a multi-AZ deployment. And note also down below there, things like my backup window, my maintenance windows that I can apply, the amount of storage that's allocated, whether this database would have an auto minor version upgrade or not. But a multi-AZ deployment takes away the pain of dealing with master-slave replication between database engines. So with MySQL, you can choose multi-AZ, and that will be a synchronous replication from the master to the replica, and will automatically fail over in the problem state and promote the replica to a master, and you can test that failure. And it will deploy across multi-AZs in line with best practice within AWS architectural design. Now that, if you did that yourself, can be quite a challenge, and it can take quite a bit of time, and it can certainly take dedicated resources in your environment. So with RDS, we can take away that pain. You can also push button scale RDS. So you noticed in that screenshot that I'd chosen an instance size, but you can scale from very small instances, and indeed RDS is available on the smallest in the free tier for you to get trying. But you can go to some of the largest instances with very high I/O, and indeed you can choose provisioned IOPS. So if you've got particularly intensive operations on a database and you need consistency from the I/O from the underlying storage technologies, you can choose to provision particular levels of I/O operations per second. And of course you can add read replicas at a click of a button, so you can offload the reads from a master database, and you can integrate with things like Elasticache, which I mentioned before, for performance. So these are all things that traditionally would take a DB admin some time to get right and to maintain and to keep up to scratch. With RDS, we take away that pain and do it for you. So it's a database as a service, no need for you to install or manage databases on EC2, and it's inherently scalable and fault tolerant in its configuration should you choose to click the button. So we support, as I said, MySQL, SQL Server and Oracle RDBMSs. You can bring your own licenses for Oracle and SQL Server if you have them already, or you can choose to have the incorporated hourly rate on those databases where we take the license paying for you. They're pre-configured, so you get started instantly. Just as quickly as you can create an EC2 instance, you can create an RDS instance and being given an endpoint which you can then start using in your applications. We'll take care of the patching, the backups, the recovery and the failover, and the replication to deal with HA deployment. Take away all the pain points for you. So RDBMS on AWS, you can of course go and install and set up one yourself, and you would set up and manage the instances in EC2 to do that. You would install and configure the database platform, so you might on Linux yum install MySQL or install an MS SQL database on a Windows instance. You then need to think about the backup strategy and create the jobs that are going to go off and take backups. You might need to do housekeeping, log management and so on as well at the same time. You're going to implement master slave if you want HA, so you have to do the job of dealing with that, whether you want synchronous or asynchronous replication. If you want performance offloading of read replicas, you're going to need to go and create new EC2 instances and then do installations and configure those to be read replicas. And then you're going to need to manage the maintenance of all of those instances you just created, not to mention the monitoring. With RDS, and you'll see a theme through this presentation, these comparisons, you simply create the instance, select multi-AZ if you want it, choose your backup retention period, choose the maintenance windows, and click go. And that database platform is then available to you to the instance sizes you've chosen, and will take care of all the things like backups and failover if we need to fail that database over. So Sega, I mentioned before, use RDS. So if there's any gamers in the audience, you probably used some of the sites that are backed by RDS. So some very popular football games and first-person shooter games are backed by RDS. So not only things like the forums, but also a lot of the media content, game metadata that drives some of the multiplayer games and the user-generated content within those games is all within Amazon RDS. And Sega use a multi-AZ deployment, and they talk about it taking away the time-consuming database administration tasks and allowing them to focus on business-critical applications, which to them is world-class content, games, and continued reliability, so that gamers can enjoy the experience whenever they want to, and it's always there. Okay, so moving on. DynamoDB. So DynamoDB is Amazon's NoSQL high-performance data store, and it's designed to solve a particular type of problem. So if you look at relational databases, the performance that we want from a relational database at any scale is consistent. So here a straight line that we would like a relational database to provide predictable, consistent performance regardless of the scale that database is operating at, regardless of the number of rows that are in a particular table, the sheer volume of data in terms of gigabytes or terabytes of storage required behind it, and the associated indexes that go with it. But in reality, as relational databases get bigger, their performance degrades, and we start having to do more work around trying to break that gap and bring it towards a straight line. So whether it be more hardware that we need to roll in, the sharding of our relational databases across multiple pieces of hardware, implementing caching strategies around it, and then you have to deal with all the things around cluster management and then the fault management of a cluster. So it becomes quite complicated at very large scales to run relational databases to get consistent performance, and I think there's a point in time at which you'll start to see this degradation. So DynamoDB was designed in order to alleviate that problem and to provide a consistency of performance on a table basis that's predictable at any scale. So DynamoDB introduced the concept of simply dialing up the provisioned capacity that you so wish behind a particular table. And other NoSQL databases out there, such as Mongo or Cassandra, operate on a similar basis. So effectively they are non-relational stores of key value pairs with particular types of indexes across them and particular sharding strategies behind the scenes that enable them to provide very high performance at very high scale. And if you look at what DynamoDB does behind the scenes, at a low provision throughput, we will take your table definition and we will place it on SSD-backed hardware within a region that you chose to run. Now, behind the scenes, what we're actually doing is putting multiple copies of that table, a partition of that table, across replicas in multiple availability zones, all backed by SSD hardware. But my diagrams will become quite complicated if I keep showing availability zones. So think of DynamoDB as a regional service that you create a table within a region, and by design and inherently behind the scenes, it is replicated and therefore an HA table. Now, as you dial up the desired capacity that you want on a table, you're simply increasing the number of read writes per second that you wish to receive by issuing a CLI command or using the console to dial that performance up. What we'll do is we'll create more or repartition your data and spread it across more physical hardware within a region, and again across multiple availability zones with replicas of all of these partitions. And because it's backed by SSD, it's very high performance, very low latency. And by doing this, we're able to provide a consistency of latency for access to your data. So DynamoDB operates at single-digit millisecond performance latencies for read writes on average, so that you can be sure, regardless of the volume of data that's in there, that if you request a certain provision throughput, we'll do the job to make sure that you can get it. And that applies as you go right up. So if you want 100,000 read writes per second on a table versus, let's say, 10, we will partition again across multiple physical devices, all backed by SSDs, across multiple availability zones in a region. Now, if you were operating a NoSQL store yourself, you would have to do that task yourself. You would have to manage a cluster to that degree. So DynamoDB is a managed NoSQL data store. You simply interact with it through provision throughput. So we asked a number of teams internally with Amazon when we were designing this and they were running the precursors to Dynamo as software, what it was that they wanted in terms of their interaction point with such a service. And it was simply the fact that as they required more performance, they wanted to turn the knob to turn it up. And that's what resulted in the DynamoDB service that we offer today. So it's predictable performance, as I've mentioned. You get average single-digit millisecond latencies because it's backed on SSD infrastructure. And we take care of all of that partitioning of data to ensure you get the consistency that or performance that we've promised. It's a strongly consistent data model as well, so that you can be ensured that you're reading the most up-to-date values. So when you push something in, all those replicas are updated before we return you a result. You can change that model if you so wish, if you're not interested in strongly consistent reads. It's fault tolerant by design across multiple availability zones. So again, if you were installing software to do this yourself, you'd have to do the multi-AZ deployment yourself. And it's integrated into monitoring, it's secure, it integrates with IAM for access controls, and it integrates into Elastic MapReduce, which we'll come on to later. So NoSQL on AWS, the do-it-yourself approach. This is what customers go through when they're running things like Mongo or Cassandra. So they'll perform capacity planning, determine the number of nodes they're going to require to support a given table or data structure. They may then define provisioned IOPS Elastic Block Store volumes, so the disks with consistent performance and instance types behind the scenes. So they'll create an EC2 environment to run this stuff. They'll then set up and manage the instances with the software on top, so installing the NoSQL database of choice. Then they'll need to start thinking about configuring replica sets across multiple availability zones. And if they want scaling to go up and down automatically, all of these things will have to be placed in an auto-scaling group, and the consideration of bootstrapping new instances as they come into services, a service comes into play. Then you get to the point of being able to define a table and then define the key strategy, which can define the partitioning behind a NoSQL store. Versus DynamoDB, where you simply define a table, define the key type that you're going to put across that table, and then choose how fast you want that table to work. And then you can start consuming the data or pushing data into that table and get advantage of the consistently low high performance, low latency, high performance. So you can see the theme here. Doing it yourself means you have to do more stuff. You have to run things in EC2. You have to manage and monitor and update them, versus just simply leveraging it as a service, an elastic service at that, service that you can start off at a very low level of consumption and therefore price and scale up as you need to go. And Shazam is an example I mentioned earlier of just that. So Shazam, the popular music tagging and sharing application that you can download for your phone, they scaled Dynamo to over 500,000 writes per second during a particular spike in demand for their service around Super Bowl in the US. So it gave them the flexibility to bring that capacity on in a short period of time. Now, they wouldn't have been physically able to do that with their own managed NoSQL store. Simply wouldn't have been time and the way that this demand hit them to do that sort of job. And they also fed EMEA, which I'll come on to later, from Dynamo with more than 1 million writes per second. So operating at a very, very large scale without having to deal with any of the infrastructure, behind the NoSQL store, but also, in this case, behind a managed Hadoop cluster. So moving through them, moving away from data and then sort of more into middleware. I mentioned Simple Queuing Service as an example before, but this I wanted to highlight Amazon Simple Workflow for you and how this works and the pain that this takes away. So Simple Workflow is a flow framework, and it effectively enables you to string together tasks to do particular jobs in your applications. So if you've signed up to Amazon Web Services, you will have gone through a simple workflow, and the simple workflow would have been to authenticate your account. You get a phone call, a little VoIP call, you type in a PIN number, and then you're identified as actually being a genuine sign up to the AWS console. And that is implemented as a simple workflow behind the scenes. And there's a long running transaction state that's managed in SWF in that case, and also the task distribution to particular EC2 nodes that do particular jobs. So whether it be the web front end handling node that's dealing with UI update, whether it be nodes that are dealing with making a VoIP call to you and dealing with the interaction over tones when you type in your PIN into the phone, or dealing with the completion of the transaction and therefore the setup of the account, sort of three broad steps. There'll all be different task nodes that are managed in that simple workflow. And if you look at a typical business workflow, workflows are everywhere, whether it be managing a multiplayer online game and the dealing with an in-game purchase through to a traditional transactional process on an e-commerce site such as this. They have multiple steps in them and there's multiple decision points. So a decision point here being dollar or euros. Was the order placed in one or other currencies? And then that drives different processing routes, and then the steps involved do something against some data in some application. And typically they're over heterogeneous systems. So here we're seeing the update inventories on system A versus updating a dollar account in system B, and then so on and so forth. So ultimately ending up here in sending an email via an email sending system, a different application running on different environments typically. So state is a thing that's managed typically in the endpoints in such a process. So and project logic, process logic is typically embedded in the applications at the bottom too. So if we look at the states here, shipping an order in system D would manage the state of that order and the shipment. State around the updating of a financial application might be handled by the node that's dealing with the update. Process logic can be embedded at the back end of an application, so updating inventory and then it embedding a simple rule that says, oh, was this a dollar or euro transaction, therefore I'll fire off a message to a given system. And then you're typically implementing middleware between these things. So shown here is a simple queue to isolate system C from system D to handle the carry of the event between the applications. So you end up with state managed in end systems, so distributed state, process logic embedded all over the place, and then you're challenged with complex queuing that you might put in between systems to decouple them, and then the issues of things like dealing with the message ordering, deduplication that might happen if you get a problem and you get two messages of the same type being generated for a given transaction. Dependencies between flows as well, and scaling and the failover. If something goes wrong, how do you fail that over and make that highly available across multiple physical facilities or multiple availability zones? So quite a complex task when you start having complex heterogeneous workflows. But you can implement that in a simple workflow, where simple workflow takes away like all the lines and the decision points into something called a decider. So shown there in yellow is all the routing and the flow we embody in something called a decider, and that's simply a piece of logic that you write that says, if I've got an event type A, what do I do with it next? And then you implement workers, which are the square blocks, that actually do some sort of task like update inventory, update an account, ship an order, send an email. And all the metadata and state relating to any of the transactions that are flowing across a workflow are pushed up into the cloud and stored in a highly durable way, similar to how we would store S3 data, or SQS data with a simple queuing service. So highly durable storage of that metadata and the state of any given implementation of a workflow or execution of a workflow. So looking at that slightly differently and see how simple workflow works is that you implement a decider and it simply polls the workflow service to say, have you got any decisions for me to make? And this is something that you write. Again, you can write it against a number of our APIs, but a very simple set of APIs where you write a logic in the chosen language that you wish to run in. So this might be to say that a process step has completed, and that based upon the outcome of that processing step, the decider will say, move this execution onto step A or B as a result. And it will post that result to say, I've moved and made a decision on. And worker tasks poll simple workflows and say, have you got anything for me to do? So a worker task might be encode video, or it might be send email. Simple worker that's polling to say, do you have any jobs of this particular type for me to do? Because if you do, I'll pick one off the queue and I'll do it, and I'll tell you when I'm finished. And if I don't finish, the simple workflow service will handle all those failures and ensure that rollback occurs and I get consistency across the workflow. So workflows on AWS, you can obviously do this yourself, and there are many frameworks for doing this yourself. So again, you would set up and manage instances, install the software to do the job, architect that for high availability, and then you get to deal with the implementation of the workflow. So this could be visual workflows in a high-level UML-like language, or it could be a BPML definition, a complex XML form. And then you get to implement the process and the audit around that process to ensure that things are happening to your business's satisfaction. And that can get quite difficult, and it can become quite complex in terms of having to learn new technologies, and particularly languages, to define those workflows. Versus simple workflow, when we asked our customers what they wanted from a workflow engine, was fundamentally to implement the decision logic in a language of their choice. They wanted to use the language that they use for all their other applications to define a simple set of workflow logic, a simple decision tree, and then to implement task workers against a very simple API to get a job, and then to say whether that job is complete or not. And that's simple workflow. And it's been used in a whole host of use cases, but this one's probably the most exciting use case, which is the Mars rovers, and Curiosity included in this, even though this is the old rovers. And what happened is that these rovers have stereographic cameras on their on the stalks that you saw there at the top, and they take images from those cameras and take left and right images, and they perform a warping operation, and then they need to stereo match those images and then produce a 3D map which enables which can get tiled so that an operator on Earth can get a good grip on where that rover is and make a decision on where that rover should go next. And the resulting images look something like this. Obviously with 3D goggles they'd look a lot better. But that was a simple workflow coordinating various steps in the management of images from the rovers. And in this case they actually incorporated both EC2 assets to do various tasks in that workflow with existing on-premise assets that were configured to do particular tasks, because simply they're polling to the simple workflow work service to get some tasks to perform. And that can be an EC2 instance that's doing that polling, or it could be an on-premise server. So moving on to more application-orientated frameworks, Amazon Cloud Search is search wrapped as a service. Now, if you're operating at a low level of scale, you might be able to get away with a very basic search such as this, a select statement on a database. But as you start getting up the volume tree, so 1 million hits a day, 5 million objects in a database, that doesn't quite cut it. And actually searching for things becomes quite a tricky task to perform. Typical projects would be, firstly, to do a lot of educational research, buy a book on search, because the search technologies out there, particularly open search technologies or even the commercial ones, are very complicated behind the scenes. You then have to plan a POC. Is this search engine going to work for me? Train some people in how these search engines work, buy some hardware, install the software on that hardware, tune it, because everyone's search problem is different and the way the indexes need to be managed can be different. And then you're into production, you need to think about scaling the hardware as your search volumes go up or your data goes up, and then you rinse and repeat, tune software, scale hardware, and go around in a circle. Now, with Cloud Search, you can not do all of that, and you can simply integrate search as a service. So integrate some simple endpoints into your application as opposed to having to do all the management of the environment yourself. And Cloud Search is built upon A9, and A9 is the same search engine technology that is behind the Amazon retail site. So what we did is we took the software that we run ourselves and have been doing for 10 years or so, and then wrapped that in the same principles of AWS, which is to make it on-demand, pay-as-you-go, elastic behind the scenes. So we've taken the A9 technology and called it Cloud Search by putting it into AWS. And if you look at what a search is, search has got a number of facets to it, and facets, pardon the pun, because facets is one of those aspects, if you like. So down the bottom left, a facet, if you go on to Amazon Retail and search for something, you'll see groups of objects by department, color, material, and counts of objects that fit into those groups. So they're the facets. You get fielded, so you get groups again at category level that you can drill down into. You have to deal with the tokenization of the search term to make it effective to be searched across. And then, of course, you get results. And then the ranking of those results is important because you might have different data that wants to drive different sorts of ranking. You might have promotions. You might have user reviews that would drive the ordering of how these things are brought back and displayed to a user. So that's the anatomy of a search engine. And within AWS Cloud Search, all of that functionality is provided through two very simple endpoints. So simple endpoints in terms of where you stick data, where you upload your documents to be indexed for search, and then the endpoint from which you then can search the documents that you've inserted into your Cloud Search domain. And you will get all of that faceting, all of that fielded rank ordering of results. You get the tokenization of the search terms as part and parcel of using the service against the search endpoint. So you can try Cloud Search, and there's a free trial available for Cloud Search at the moment. So if you want to have a go, you can upload some documents and then you can use the test UI within the console. So you can see here that I've created a search against my own search data set. On the right I've got my facets being returned, and I've got my results in the middle there for a search for over a particular data set. And the example that I've just run there was actually behind the scenes is hitting an endpoint against my search domain. In this case, I've got a toilets in Oz search domain for a little mobile application to find a toilet when you're traveling. And it's hitting a search domain there and firing in a query string and then some search options. So a simple web service call that would return a JSON object. So in this case, it's returning the hits that it's found, some information about the computation time around those hits. And then the return results can be configured based upon the options that I fire into the search endpoint. Now, cloud search is scalable, so if you were implementing search yourself, you would have to deal with, just like NoSQL databases, deal with a lot of clustering and scaling challenges to make sure that you get consistent performance. Now, with cloud search, if you took an example over time, and this might be a retail organization at a particular peak day within the week where users are coming on and doing a series of online shopping, and you need to scale up the capacity you have behind your search engine to keep the performance consistent. We might see that I've got a search instance which is managed by Cloud Search here with a partition and a copy of my data. So I've got a single copy of my data and I've got a single partition handling my search index. And when that instance hits or sat below 80% CPU, I'm sat on a single instance. And when I go above 80% CPU, for example, Cloud Search will automatically create a new copy of my data, of that partition, and then copy it onto a new instance, in this case a small instance. So I get two small instances now with two copies of my data, so I'm able to create double the capacity behind my search engine. And so on. So I get three copies here, all spread across instances of small size. Now these instances could be extra large EC2 instances for even greater capacity. The point here is that when I get to midnight and everyone's done with their shopping spurt on a Friday evening or a Monday evening, the partitions or the copies are taken away and I'm reverted to my single small instance, which is reducing my costs. So traditional required capacity, if I was doing something like Solar, I'd have to deal with three instances and the three copies of my data in order to handle that capacity demand. Elastic capacity goes up and down, and therefore I make savings in terms of the cost because I'm running less EC2 instances. Now Cloud Search manages all of that for you behind the scenes so you don't have to touch it. And what it actually does is that as your traffic volume and complexity increases, we will create more copies. So shown here is search instances that can be of various different sizes up to the large instance types we have running in EC2. It will create n numbers or n copies of your data and spread them across instances to handle the number of requests that are coming in. So effectively, load balancing across search instances, all with a copy of the same search index. Also, if your document quantity, so you're putting very large volumes of data up into Cloud Search, we will create partitions on the data. So here I've got the same data set, copy one, but a number of partitions spread across instances. And this thing goes in a matrix. So if you get very large data volumes and very high traffic requests, you can end up in the bottom right there where we've got n partitions of your data and n copies of your data, all managed across EC2 resources behind the scenes. And you don't have to manage any of that. Now doing that yourself, you would have to manage that stuff yourself. So search on AWS, doing it yourself, you need to, again, just like in NoSQL, you need to perform capacity planning, work out the sort of size of the indexes that you may have, are they going to fit on one instance or not. You're going to set up and manage the required instances, install an open search software such as Solar maybe across that cluster. You're going to need to manage the cluster partitioning of data and size over time and think about whether you want that to auto scale or the scripting you're going to need to increase capacity and the configuration tasks you're going to have to take to ensure that cluster is consistent and has integrity. And then you're going to need to monitor it and find out what's going on. Whereas Cloud Search, and I encourage you to have a go in the free tier, because the free trial I should say, because it's a great service to use, great fun to configure and play with. You'll create a search domain in the console. You simply upload documents, and these can live in S3 or you can upload them through the API or the console. And then configure the indexes you want to put on it, what you want to return in the search result, and then retrieve the results from the endpoint that's defined. Now behind the scene, Cloud Search will deal with all that scaling, repartitioning of data, and it will actually go off and generate elastic MapReduce jobs each time it requires to recomputate the cluster size and respread the indexes. So a sophisticated set of technologies behind the scenes that's presented to you in a very simple and abstract way to use. And SmugMug was an example. So SmugMug, there's a search box. Everyone knows what a search box looks like. But down the left are these facets. So just as in Amazon Retail, my umbrella example, I had different types and groups of umbrellas and accounts. Within here, I've got the metadata associated with the photos as facets. So looking at aperture size there, the number of photos that have been taken with particular aperture sizes, or the date that something was taken. A complete sort of direct mapping really from the technology behind Amazon Retail into a completely different use case using Cloud Search. Now, lastly, today, I'm going to look at Amazon Elastic MapReduce as another managed framework for doing analytics. And it really drives off this equation. So 1 instance for 100 hours equals 100 instances for 1 hour. They cost the same on a small instance. That's $8. So 1 instance for 100 hours, 100 instances for 1 hour. So you can use 100 instances for 1 hour for $8. And Hadoop is a framework that can take advantage of this, and this is a logo for Hadoop, and we call that Elastic MapReduce. So Elastic MapReduce is a managed Hadoop cluster that enables you to split up a computational task across many instances, taking advantage of that equation of 100 instances for 1 hour costing the same as 100 hours of one instance. It's a comprehensive framework that supports languages like Hive and Pig, and you can define your logic in various languages, and it integrates with spot pricing. And that's an important thing that we'll talk about when I go through how it works. But what really is EMR? Well, it's a framework that splits your data into lots of little pieces, spreads those across multiple EC2 instances to allow some sort of processing to occur, and then it gathers the results for you to see. So the map process is where it splits the data out and processes it. The reduce is how it brings the data back together. Elastic MapReduce. So if you take an example of a very large data set, you might have an application log, click logs, user activities on your website in terabytes of size. Lots of instances of X in there that you want to find out. These might be actions by particular users, for example. You would split that log into many small pieces and spread them across an EMR cluster. They get processed across those EC2 instances, and then they aggregate the results from all the nodes, and you get an aggregate view of X. And with EMR, because you could do that on 10 instances, 100 instances, or 1,000 instances, you can get that insight in a fraction of the time than you would if you only had one instance to process that very large data set. So take advantage of that equation and price. So 1 instance for 100 hours, 100 instances for 1 hour is $8. But you can go 1 instance for 1,000 hours or 1,000 instances for 1 hour for the same price. There's a tenfold increase. So on a small instances, that's $80. So 1,000 instances processing a data set in parallel will cost you $80, and you can achieve in an hour what you would normally have to wait 1,000 hours to get the result from. So looking a bit more detail of how that works, you can take input data from a number of sources, but S3 is a common one. So S3 being the highly durable storage platform, simple storage service. You pop your data into S3, and then you write a piece of code that you're going to drop into Elastic MapReduce. So you can use various different programming languages, and this might be a simple routine that's going to count the instances of a particular record type in a log. So it might be simple string searches within a log. Drop that piece of code into Elastic MapReduce, and behind the scenes we'll go and create a Hadoop name node. This is the controller of a cluster, and then we'll create an Elastic cluster based upon the specification you say. So if you say I only want 10 instances, or I want 1,000 instances, and if you want them to be destroyed automatically at the end, you can just set these up in terms of setting a job up in EMR. Those will be populated with the data from S3 across a distributed file system, Hadoop file system. So all those instances have access to the data required to do the job. And then when you've got that set up, you can actually use queries against it. So you can use like JDBC on top of Pig and Hive to actually query that distributed data set if you want to. But ultimately, you're going to process the code that you've dropped into EMR and generate some sort of output, which you can stick into S3 or SimpleDB. And it all integrates with DynamoDB as well, as I mentioned before. And what you end up with is that if you say destroy the cluster on complete, is that when the job's done, you end up with your source data and your output data, and you've done it in a time frame that makes sense to you depending on how much you want to spend. And if you use Spot, the perverse thing is that you can actually use Spot to get a much reduced price on the instances, and because Hadoop is inherently fault tolerant, you can actually do things quicker for cheaper by using spot pricing for instance types. So Hadoop on AWS, again, you'd need to configure and manage your EC2 instances, set up a name node, set up some data nodes that are going to do the job, create a file system across all those nodes, format that file system, set up the extras you might want. If you want to query it with Hive or something like that, you're going to need to go and set that up across all that cluster. You need to prepare your data and push it onto that distributed file system, and then execute some sort of job. With Elastic MapReduce, you specify the desired cluster size, drop your code in, and execute the job. And that really is how simple EMR is. And again, you can get going with EMR. I'll come on to a program that gives you some credits to have a go with it. So Yelp uses EMR, and they pre-process files behind their web application which generate things like the people who viewed this also viewed that, review highlights, autocomplete files based upon what people are typing. So they're constantly running EMR jobs to generate content which sits behind their web application to make it look like things are dynamically being generated. And they are, but they're very computationally intensive jobs on very large data sets that require an EMR cluster to produce some effective things that improve the user experience for their web application. Razorfish do as well, and they talk about the ability to use EMR to get insight in a timely fashion meant that they're much more effective in the advertising campaigns they run on behalf of their clients, and they could do it with no upfront investment in hardware or the dealing with finding specialists in managing Hadoop clusters and distributed file systems. So where to go next? You can go to our TypePad blog. So all of the stuff here, you'll find that there's rich blog on aws.typepad.com and my colleagues blog on the technology as it gets released. And of course, there's white papers on a number of these technologies and approaches to using things like SQS in your architectures in terms of cost optimization angles and using services instead of software. But you can also go to powerof60.com, which is a little microsite hosted by Intel and AWS, where you can get $100 of credits for free to try out doing some computational analysis with EMR. It's approximately 600 hours of EC2 instances for $100 on a small instance, and you can spin up some EMR jobs that I'd mentioned before to give you a feel about how you would do that sort of job, upload some data that you might have internally, and see how you fare. So you sort of get into the big data space. So $100 of free credits, just fill out the simple form at that website. So in summary, AWS is more than compute and storage. And the previous webinars that I've done in this series have really focused in on the use cases about consuming EC2 resources or storing data in the cloud and the application you can build on it. And today's webinars really introduce you more to the idea of running databases, middleware, and complex frameworks as a service. So of course you can go off and install and run your own software. And there'll be software that you need to do that because they aren't wrapped as a service. And of course you can do that. But I encourage you to look at the frameworks that we provide as a service because they will reduce the operational burden that are placed upon your teams in running all those ancillary pieces of software. And it gives you access to scalable and sophisticated software without the overheads, right? So think scalability, think reliability of software that you need to build your applications around. Using them as a service that operate at a regional level, you'll inherit the properties of the AWS cloud. So just as S3 is a highly durable store for your data, things like SQS, simple workflow, build upon those highly durable storage mechanisms to give you a higher level application functionality at a very low price point and all the elasticity that comes with it. And of course, aws.amazon.com is where you can go to find out more.